Okay, so we're up to the last one for module one. So this is chemical networks. Our syllabus is our outcome is to investigate elements that possess the physical property of allotropy, as well as investigate the different chemical structures of atoms and elements, including but not limited to ionic networks, covalent networks, including diamond and silicon dioxide, covalent molecular and metallic structure. So let's have a look through this stuff. So firstly, have a go at the revision questions. So here we have the answers. So the shapes of simple covalent molecules depend on the arrangement of electrons around the atom. VSEPR theory, so valence shell electron pair repulsion theory, indicates that electron pairs move as far away from each other as possible. To draw the molecular structure, you need to first draw the Lewis structure. So let's have a look at what we're doing today. So chemical networks. So while most substances are happy to exist as individual molecules, there are some that prefer to exist in continuous 3D structures called lattices or network structures. So some can be called crystal lattice structures, but not all of them. So today we'll be examining metallic, ionic, and covalent lattices. So firstly, metallic. When metals form solids, the atoms pack tightly into metallic lattices. The atoms are close enough that the electron orbitals overlap, and the electrons are effectively shared between all of the metal ions. And this forms what we call a delocalized sea of electrons. So what we mean by delocalized is it's not local to one spot. So it's not in one orbital. They kind of all overlap. They just kind of move around. So it's why when we apply voltage to a metal, we can actually get electricity flowing through it. So electrons flow out of one end into the other. They just kind of all flow through this metallic lattice. So here's an example. We have our positive ions with our negative charges. So normally a positive ion with a negative electron around it, it's just a neutral atom. But we've got them kind of flowing all about in between each other. Okay. Now this relates to the properties. So one of the properties is that metals are hard and have relatively high boiling points. And that's just because of the strong electrostatic attraction between the positives and the negatives. It keeps it all nice and bound. And the delocalization actually stabilizes that structure. Metals are good conductors, so as I was saying before, because of this delocalized sea of electrons, if you take some electrons out of one end, then electrons will flow into the spots, and then they'll flow in the other end. So it allows that conduction of electricity. Now, the other thing with metals is they're malleable and ductile, so they can be reshaped quite easily, and they can also be drawn into wires. Now, the reason for this is that when a force causes layers to move past one another, they still hold together. So we'll see with the ionic ones, it's a bit different. But because of that delocalization, that stabilization, um, we can actually kind of move the atoms around and deform it. Okay, onto ionic lattices. So ionic solids arrange themselves into repeating structures called ionic lattices. Generally, the lattice contains alternating anions and cations in 3 dimensions. So that's what this looks like here. So basically we have a cation, and all around it will be anions, and then all around each of those will be cations, so on and so forth. Now, due to the large electrostatic attraction between the ions in an ionic lattice, ionic solids have a high melting point and boiling point. They can't conduct electricity, and they easily dissolve in water. Okay, so that's another reason why they have that high boiling point, because the lattices hold them together quite easily. Now, covalent lattices are also called covalent network structures. They're 3D arrangements of atoms that are bonded through covalent bonds. They're generally very strong with high melting points. And some of the elements compounds can exist in multiple different types of covalent networks, and these are what we call allotropes. Okay, so if we ever hear the term allotrope, that is a different arrangement of the same type of atom or compound. And the most common example is carbon, which can exist in several different forms. Now, in your booklets, I've put some pictures, but they don't really do the different structures justice. So I've got some GIFs on the slides, so hopefully they come through okay. Now, one of the first allotropes of carbon is diamond. So it's the hardest known naturally occurring mineral. It's incredibly strong. It's made of carbon atoms tetrahedrally bonded to other carbon atoms. So basically, it's one with four around it, and then each of those is repeating throughout the whole structure. So here's some examples. So some GIFs. You can see it in the top. Sorry, in the one on the left, how it is that repeating pattern, and we just keep building the same bit on the top. I've put the one on the right in there as well, just so you can see the 3D structure. So it does kind of correlate quite well to 4 points in a cube. So that's one of the allotropes. The next one is graphite. So this is an allotrope of carbon where the carbon atoms are bonded in a trigonal planar pattern. So if you remember from molecular geometry, so it's 3 atoms around a central atom, all in a single plane. This pattern forms sheets known as graphene sheets, and they're basically just a repeating pattern of hexagons taped to each other. The lone pairs of electrons above and below the sheets hold them together, but these bonds are not very strong, so they don't hold well. That's why you can use graphite to draw on paper, because those sheets will come off. It's why you can't use diamond, because diamond doesn't have the sheets. These electrons, however, allow electrical conductivity, which is something rarely seen outside of metals. So when we say metals conduct electricity and non-metals don't, again, because it's chemistry, there's some exceptions to the rule, and one of them is graphite. Okay, so we quite often use graphite electrodes for electrochemistry just because they're non-reactive. So here's an example of some graphite. I just found this animation, kind of gives a good picture. Just hexagon sheets stacked on top of each other. Next one is carbon nanotubes. So carbon nanotubes are a tubular form of carbon. It's basically a sheet of graphite that's been rolled up into a tube. These structures also conduct electricity and have very high tensile strength. And it's the primary component of carbon fiber. So when we say carbon fiber, these are the fibers that make up your carbon fiber. Now here's some animations to hopefully show you what they look like. So it's just that hexagonal pattern kind of rolled up into a tube. And there are several different types of tubes that we can get. Okay, and they can be very long. Another allotrope of carbon is the Buckminster fullerene. We also call them buckyballs. It's an allotrope that looks like a soccer ball, basically. So we have a bunch of hexagons and pentagons arranged pretty much the same way a soccer ball is arranged. It was originally just a curiosity, but buckyballs are found using composite materials in solar cells, also has potential for drug delivery systems into certain parts of the body. So this is a buckyball, just a rotating animation just to show you what it looks like. And when I say it looks just like a soccer ball, it's pretty much just like a soccer ball. So summary for today, metallic lattices have a sea of delocalized electrons around the atoms. Ionic lattices are usually alternating positive and negative charges. Allotropes are the same atom or molecule in a different arrangement. And allotropes of carbon include diamond, graphite, carbon nanotubes, and buckyballs. So that's it for Module 1. So after this, we're going to go on and do some revision questions, do a topic test, and then move on to Module 2.